It's like everywhere you turn, there's another headline about a data breach or some crazy new cyber attack, trying to keep up with all the latest cybersecurity threats. I don't know about you, but I feel like I'm constantly trying to drink from a fire hose.
Yeah, I know what you mean. The cybersecurity landscape.
Yeah.
It's relentless. There's just so much information out there. It can be really tough to know where to focus your energy. But I think that's exactly why it's so important to pick specific areas and really dive deep, like really understand the mechanics of how these attacks work.
I totally agree. And that's
Mm.
exactly what we're doing today. We've been digging through a bunch of fresh security research, and we're going to pull out the most interesting, most important stuff. So think of it as a cheat sheet, right? You'll be in the know without having to wade through all the technical weeds.
So we've got mobile app vulnerabilities, web app security, identity systems, even email.
Hmm.
And you know what's interesting is how all these different security issues, they're all kind of connected in ways you might not expect.
All right, it all ties together somehow. Okay, let's get right into it. We're going to start with mobile application security, specifically a deep dive into an Android app that's pretty popular.
This research really shines a light on that constant back and forth in mobile security. One of the big challenges when you're trying to analyze an app's traffic is SSL pinning.
Okay, hold on. For those who aren't familiar, can you quickly explain what SSL pinning is and why it's a hurdle?
SSL pinning is it's a way to make sure an app only talks to the server it's supposed to talk to. Like, it makes it really hard to intersect the data. Usually with web apps, you can install your own certificate as a trusted authority and kind of snoop on the traffic. But with pinning, the app says, nope, I'm only trusting this specific certificate.
Gotcha. So in a way, it's like an extra layer of security specifically for mobile apps. So how did the researcher actually bypass the SSL pinning in this case?
They used Frida, a tool that lets you tweak an app's code on the fly. They wrote a Frida script, boom, SSL pinning bypassed.
Okay, so they can see the traffic now. But I'm guessing it wasn't just plain text. Sounds like there was something else protecting the data.
You got it. They realized there was custom encryption on top of that, and they figured, okay, it's probably symmetric encryption, which means the same keys used for both encrypting and decrypting. So the question becomes, how does that key get shared? Where's it stored?
The researcher noticed something in the HTTP headers. There was this X cookie header that seemed a little suspicious.
Exactly. And, drawing on experience in Occam's razor, that idea of the simplest explanation often being the right one, they had a hunch. They started by hooking all the text strings in the app's code. It's a great way to get a feel for what's happening under the hood, especially when things are deliberately made hard to read.
Hooking all strings. I mean, that sounds like searching for a needle in a haystack.
Sometimes it is, but it's worth it. They eventually found a specific piece of code that looked like it was doing the encryption and decryption dance. More digging, including a universal AES hooking script, and they cracked the code, they decrypted the traffic.
So finally, they could see what was being sent back and forth. But wait, there's more. Right. Even with the encryption broken, the data, especially sensitive stuff like phone numbers, it was still kind of scrambled.
Yeah, exactly. They saw the phone number, but it was transformed into this weird string. But they're persistent, right? They kept debugging, analyzing the code, and eventually they figured out the encoding method. They wrote a script to decode it.
All right, so they jumped through all those hoops, bypassed the SSL pinning, decrypted the traffic, decoded the data, and now they can finally see the plain text conversation. Now it's time to actually look for vulnerabilities, right?
That's exactly what they did. They shifted into threat modeling mode. That basically means thinking like an attacker, looking for classic web app weaknesses. Insecure direct object reference, IDR, SQL injection, logic flaws, all that. They spent a good chunk of time on this, but at first glance, nothing obvious jumped out.
Man, that's got to be frustrating, putting in all that effort and then hitting a wall. But they didn't stop there, right? They noticed this weird pattern in the HTTP requests.
That's where things get really interesting. They saw this pattern, wgt.filepath, FUNC, RGS. And that's a big clue, right? It looked like the server was taking a file path and then executing a function from that file with whatever arguments you gave it, almost like a way to run code remotely.
So, first thought, local file disclosure, try to read some sensitive files directly from the server.
Exactly. They tried hitting common targets. Echoes that set it past teep speed. No dice. Then they tried fuzzing the function names, the parameters, even injecting basic JavaScript, console.log, document.write, nothing. Likely the server had some kind of validation in place, checking what functions you could call from which files.
Makes sense. Basic security hygiene, but then how did they pull off the remote code execution?
They went out of band. Instead of trying to get a response back through HTTP, they tried to trigger a DNS request to a server they controlled. And guess what? They saw DNS logs coming from the target server. That meant they could make the server talk to the outside world.
Hold on, why DNS? If they couldn't get through with regular HTTP, what made DNS different?
This is key. The researchers figured the target app was probably running in an environment that used Active Directory AD. That's super common in enterprise setups. You've got internal DNS servers that handle names within the network and external ones for the public internet. But devices inside the AD network usually only talk to the internal DNS server. And if that server can't resolve a name, it often asks an external one.
So the vulnerable server, sitting inside this AD network, it gets this malicious request. It tries to resolve the attacker's domain name. And because it can't find it internally, it asks the outside DNS server, bypassing whatever restrictions were blocking HTTP. It's like your office phone directory doesn't have the number, so it has to dial the operator.
Perfect analogy. So now they can exfiltrate data via DNS. They encoded data into subdomains of their controlled domain. They even had this clever trick. They replaced slashes and file paths with Z and then converted them back when they received the DNS logs.
That's pretty ingenious, but DNS, it's not really made for transferring large amounts of data, right?
Yeah, that's true. DNS queries have length limits. They mostly use UDP, which isn't reliable, and you have to break the data down into small chunks. The researchers even went into the nitty-gritty of encoding and reassembling the data, dealing with packet loss, the whole 9 yards.
And the story doesn't end there, does it?
Yeah.
There's something about a post-authentication feature that was also potentially problematic.
Right. So after logging in, they found this feature that let them call an internal web service directly. No extra authentication, no authorization checks. This meant you could potentially do stuff like sending SMS messages using the app's legitimate sender identity. Really shows how important authorization checks are, even for stuff that's internal.
Yeah, that's a good point. Wow, that's a deep dive into one mobile application. It really shows how attackers think, right? Layer by layer, finding unexpected ways to chain vulnerabilities together. Okay, let's change gears. We've talked about a specific mobile app vulnerability. Now let's zoom out to a broader web security concept, server-side request forgery, or SSRF. Usually we think of SSRF in terms of the classic risks, finding stuff on internal networks, maybe executing code on those internal systems. But there's another less common way to think about SSRS.
And what's really interesting here is how you can potentially use SSRF to take over someone's account, even if you can't get directly into the internal network.
Account takeover via SSRF. How does that work?
Think of it this way. Even if you can't directly talk to the juicy internal services because of network segmentation or whatever, you can potentially manipulate how the server interacts with external services. For example, imagine you combine SSRF with phishing. You could use SSRF to make the server send an email to a victim. That email looks legit, and it tricks them into doing something that compromises their account. Clicking a bad link, giving up sensitive info, you name it.
So you're not directly attacking the internal infrastructure. You're using SSRF as a way to pull strings indirectly and target user accounts through external interactions. That's a really clever twist on the classic SSRF scenario. All right, let's move on to another attack that's pretty innovative, cross-window forgery, or double-click jacking as it's often called. This one sounds particularly sneaky.
It is, and the crazy thing is it bypasses a lot of the defenses we usually rely on for clickjacking protection. It leverages the standard HTML feature where you can use the innate attribute of an element in the URL fragment to pre-select or focus that element. Like if a button has a specific ID and you include that ID in the hash of the URL, like #mybutton, that button automatically gets focused when the page loads.
Oh yeah, I've seen that used for linking to specific comments on a page. Never really thought of it as a security risk. So how does double-click jacking exploit this?
Okay, picture this. The attacker creates a tiny pop-up window. It opens the target web page, but it sneakily includes the ID of the sensitive button they want you to click in the URL fragment. So this pop-up is probably disguised as something harmless, double click here to continue or something. But the trick is the first click, when you press down the mouse button, that closes the pop-up window. And then the second click, it lands directly on the button on the page underneath.
Ah, I get it. It's all about misdirection. You think you're clicking on the pop-up, but you're actually triggering an action on the page behind it. And this can even bypass defenses like X-frame options and content security policy.
Exactly. Those traditional clickjacking defenses, they're mainly focused on preventing websites from being embedded in iframes. Double clickjacking doesn't use iframes, it uses separate windows. It can even get around same-site cookie restrictions because from the browser's perspective, you initiated the action even though you didn't mean to. And get this, it's not just limited to websites. The research suggests it could also affect browser extensions and even mobile apps through something called double tap.
That's a little unsettling, to say the least. They mentioned platforms like Coinbase and Yahoo as potential targets. How could an attacker use this against them?
Well, in those cases, they were relying on predictable button IDs for their booth flows, for authorizing apps. So an attacker could create a malicious app that asks for certain permissions. And then, using double clickjacking, they could trick a user into clicking that authorize button on the real OAuth consent screen without even realizing it.
Wow. So I'm on this attacker's site, I hold down a key, this little window flashes up, asking for a double click, and bam, I've authorized some malicious app. That's incredibly subtle, so how do you defend against this?
The research recommends a pretty clever mitigation using JavaScript. You initially disable important buttons and only enable them once you detect real user interaction, like mouse movement or a tab key press. This makes it much harder to automate or trick those actions.
Sounds like a good band-aid for the short term. But what about a more robust, long-term solution?
There's been talk about introducing a new HTTP header, maybe something like double-click protection, strict. That could tell the browser to be more careful about rapid context switching between windows during a double click, or maybe enhancing content security policy to cover these scenarios. But for now, that client-side JavaScript trick seems to be the best immediate defense for developers.
It's amazing how these tiny little browser behaviors can be chained together to create these huge security holes.
Hmm.
Okay, let's switch gears again. We're going to talk about cybersecurity in a totally different domain, one that's becoming super important: the world of electric vehicle charging infrastructure.
It's a hot topic for sure. And as the number of EV charging stations grows, so does the potential attack surface. The research points to ransomware as a major threat. Imagine attackers locking down charging stations, demanding payment to unlock them. That could cause chaos, disrupt businesses, hit people's wallets, you name it.
Talk about a nightmare scenario. It could seriously undermine trust in the whole EV charging ecosystem. What other threats are out there?
Attacks on the power grid itself are a serious concern. If attackers can manipulate the charging behavior of enough stations simultaneously, they could cause huge spikes or dips in demand, potentially destabilizing the grid. Imagine rolling blackouts, all because someone hacked into charging stations. And then there's physical access. Charging stations are often out in the open, and they might not have the best physical security. That means attackers could tamper with the hardware directly, plant malicious devices, steal credentials, who knows?
Yeah, physical security is something we don't always think about when we're talking about cyber threats, but it's obviously crucial here. And what about network-based attacks?
That's another big one. Misconfigurations can accidentally expose charging stations to the internet, making them easy targets. Or there could be weaknesses in the backend systems, like cloud portals, operator backends, remote support tools. Once they compromise those, attackers can potentially move laterally within the entire infrastructure.
So it sounds like we've got a bit of a security headache here. Are there any regulations or guidelines to address these risks?
Actually, there are some new regulations coming into play. The NIS2 directive and the EU Cyber Resilience Act, they both have implications for EV charging infrastructure. NIS2 basically says that operators of essential services, which now includes charging point operators, they have to implement proper security measures. And the Cyber Resilience Act, that's all about making sure the products themselves are secure. So manufacturers need to follow security standards during development and do regular vulnerability testing, including penetration testing.
So what specific security measures should operators and manufacturers be focusing on to protect this infrastructure?
Penetration testing is absolutely essential, and it needs to be comprehensive, covering every aspect of the system: the hardware, the software, the firmware, any physical access points, and the entire network. On the hardware side, you're looking for things like missing secure boot, lack of encryption, any debugging interfaces that are accessible, default or backdoor accounts, all that. The backend and cloud components, the OCPP servers, the remote support tools, the billing portals, all that needs to be tested thoroughly too. And then network penetration tests. You need to make sure the communication between the charging stations and the back end is secure, that the operator's network is properly segmented, that their firewalls are effective, and, simulate what might happen if an attacker does manage to get in. And finally, it's important to do a gap analysis to make sure you're complying with all these new regulations like NIS2 and the Cyber Resilience Act.
Wow. It sounds like taking a proactive and holistic approach to security is absolutely vital when it comes to EV charging infrastructure. I mean, this is going to be a critical part of our future, right? It affects individual users,
Yeah.
and it's tied to the power grid, which is a huge deal. Okay, let's dive into something a bit more technical. SQL injection, but with a twist. We're not talking about the kind of SQL injection you see in web apps. This is about injecting SQL at the protocol level. That sounds pretty advanced.
It is. This research is fascinating. It looks at how weaknesses in those underlying communication methods, the actual protocols databases, use how those can be exploited. This isn't your typical web app SQL injection, where the vulnerabilities and how an app handles user input.
So instead of injecting through a web form or an API, you're going deeper, messing with how the application talks to the database directly.
Bingo. A lot of these protocols, they're binary. They use very specific structures to organize the data. Delimiters, length fields, type length value formats, things like that. The research looks at how you can manipulate those structures to sneak in extra SQL or change existing commands.
They mentioned PostgreSQL as an example.
Mhm.
How does this kind of attack work against that?
PostgreSQL uses a type length value structure. Every message starts with a byte that says what type of message it is, then a 4-byte integer that tells you the total length of the message, then the actual data. And they found a vulnerability in PGX, a popular Go library for PostgreSQL. The vulnerability is an integer overflow. Basically, when the library calculates the length of a message, it can screw up if the message is big enough.
An integer overflow. I mean, that's just math, right?
Yeah.
How does that turn into a security vulnerability?
Well, when PGX gets ready to send a message, it calculates the total size, and it stores that size in a 32-bit integer. But because of how integers work, if the message is too big, the calculated size can wrap around to a much smaller value. It's like trying to pour a gallon of water into a pint glass, it overflows. So you've got this mismatch. The message is huge, but the declared length is tiny. And that gap, that's where the attacker can slip in their malicious SQL. The database sees this manipulated length and thinks, okay, this is the end of the legitimate message. But then it keeps reading, and it hits the attacker's code, and it executes it.
So even if the app is only trying to send a harmless query, the attacker can tack on their malicious code using this overflow trick.
Yeah.
Sounds like a recipe for disaster.
It really is. This could give an attacker the power to read, modify, delete anything in the database, just like regular SQL injection. And the research even goes into this technique called trampolines, where you can actually use the length bytes themselves as valid message type identifiers, so you can craft even more clever payloads.
This seems like a really low-level attack. Is it actually practical in real-world scenarios? I mean, most web apps have limits on how much data you can send, right?
Yeah, that's a fair point. But the research highlights that there are ways around those limits. Some endpoints might not be as strict, or you can use compression to squeeze more data in, or you could use things like WebSockets, which might not have the same restrictions. They even found a specific case in Harbor, a container registry project, where the default configuration was actually vulnerable to this PostgreSQL protocol level injection.
And they also talked about MongoDB.
Yes. MongoDB's protocol also has a length field at the start of each message. It's a 4-byte integer. And they found a similar integer overflow vulnerability in the Mongod Rust library. Again, you could manipulate the length, inject your own commands.
Were there any unique challenges with crafting the MongoDB payloads?
There were. You had to avoid certain bad bytes that the MongoDB parser would choke on, and you had to make sure parts of your payload were still valid UTF-8. But they found a way around that. They used metadata within the MongoDB document structure to introduce those invalid bytes that they needed for the overflow.
Wow. It's wild how vulnerabilities can pop up, not just in the application's logic, but in the fundamental communication protocols themselves. This really highlights the need for secure development practices at every single level. Okay, let's move on. Client-side path traversal, or CSPT, and how it can be combined with cross-site request forgery, CSRF. We all know about server-side path traversal, right? Where you try to access files outside the intended directories. But client-side path traversal, that's a different beast.
It is. Client-side path traversal, it's all about exploiting weaknesses in the front-end code of a web application. You're not trying to break out of the server's file system. You're trying to trick the application into making requests to the wrong parts of its own back-end API.
So you're not reading local files, you're manipulating how the app itself talks to its own backend.
Exactly, and the researchers talk about these concepts of sources and sinks. The source, that's where the vulnerability is, like in a URL parameter or a setting that gets used to build an API path. The sink, that's the code that actually makes the API request using that manipulated path.
And how does this client-side path traversal then lead to things like CSRF?
Okay, even if the attacker can't directly control the method of the request, like whether it's GET or POCA or the headers or the body, they can still chain CSPT with CSRF to do things that change the app's state on the server. A common scenario is when you have a GET request that's vulnerable to CSPT. Even if the GET request itself isn't used for a sensitive action, you can combine it with something like an open redirect vulnerability. So the manipulated GET request redirects the user somewhere else, maybe to a different part of the app, maybe to a completely external site controlled by the attacker that could leak info or set up a further attack.
So it's like taking a client-side vulnerability and using it to trigger a server-side change, even if it's not a direct PST request. That's pretty clever. The research also mentioned something about chaining one CSPT with another.
Right, so imagine you've got a GET-based CSPT that lets you control the value of an ID parameter in a JSON response. And then you have a separate post-based CSPT that uses that ID. So now you can trigger a state-changing action through this chain. They also talked about how file upload and download features can be abused. You could upload a JSON file with a manipulated ID and then use the GET-based CSPT to trigger the download of that file. And that download then triggers the post-based CSPT because the data is embedded in the file.
It really highlights how important it is to look at the whole application flow and how all these client-side and server-side things can interact in weird ways. Okay, next up, something called hijacking OAuth flows via cookie tossing. Now, cookies are at the heart of how web apps handle user sessions, right? So messing with them during an OAuth process, that sounds pretty bad.
It can be. To understand how this works, let's refresh our memory about HTTP cookies. You've got attributes like domain, path, same site, secure, HTTP only. The domain attribute is the key one here. It says which domains can access a cookie. And here's the important part. A parent domain can set a cookie that all its subdomains can access, like, domain.example.com, but it can't explicitly set a cookie for a specific subdomain, like blog.example.com. That's a security feature. It stops a less secure subdomain from messing with the cookies of a more sensitive parent domain.
Okay, so there's a boundary there for security reasons. So how does this cookie tossing attack exploit that?
Here's how it works. An attacker, let's say they control a subdomain or even a completely different domain if the target app's using a really broad domain attribute on its cookies. The attacker sets a cookie with a domain that overlaps with a legitimate user session cookie on a different subdomain. And because their cookie has a broader domain, it overrides or interferes with the real cookie.
Okay, I'm following so far. But how does that lead to hijacking an account during OAuth?
Let's say you're logged into a service like Gitpod, and you want to connect your account with your GitHub or Bitbucket. That's an oath flow. During that process, there's a whole back and forth of cookies between Gitpod and the Git provider, handling the authentication state. Now, an attacker, they might have some malicious workspace running on a Gitpod subdomain. They can use JavaScript to toss a cookie with a broad domain attribute, like .gitpod.io, and that cookie contains their session ID for Gitpod. So now, if you go through the oath flow, Gitpod might accidentally use the attacker session cookie during a critical step, and bam, your Git account gets linked to their Gitpod account, not yours.
Yikes. You think you're linking your own accounts, but behind the scenes, it's all going to the attacker. That's pretty sneaky. The research specifically mentioned Gitpod, right?
Yep, they actually pulled off this attack against Gitpod's oath flow for both GitHub and Bitbucket. They tossed a cookie called Gitpodio WT2, and they were able to get into any repos that the victim had access to. Push code, modify the source, all that.
That's bad news. So how do you protect against this kind of cookie tossing?
One really effective way is to use the host cookie prefix. Cookies with this prefix are only valid for the exact domain they were set on, so subdomains can't touch them. That pretty much shuts down this whole attack. The research also points out that JSON-based APIs, if they're relying solely on cores for security and they're not using proper anti-CSRF tokens, they're more susceptible to these kinds of attacks.
It all comes back to good security hygiene, right?
Yeah.
Properly configuring cookies, using anti-CSRF tokens, all that good stuff. Okay, let's shift gears again. Now we're going to talk about something that's more relevant to, the red teamers, the pen testers out there, attacking authentication systems, and specifically identity providers, or IDPs. This is valuable intel for anyone doing security testing.
It is. And of course, it's important to be responsible when we talk about offensive security techniques. But understanding how attackers target these systems is absolutely crucial for building better defenses. And the research points out that these attacks are happening in the real world, like the MGM breach. They used social engineering against an IDP, and the APT29 Sunburst campaign, they were forging SAML tokens. This stuff's serious business.
So what are some of the techniques red teamers are using to target these identity provider systems?
The research talks about spoofing the agents associated with popular IDPs like OneLogin and Ping-On. You basically reverse engineer their communication protocols and you try to extract sensitive data, API keys, user lists, and sometimes even plaintext LDAP credentials.
Plaintext LDAP credentials. That's a pretty major security fail.
It is. The research says that in certain configurations, the Ping-On agent might actually receive LDAP credentials unencrypted. That's like gold for an attacker. They could use that to pull off all sorts of nasty stuff like Kerberos, pass the cache, or silver ticket attacks, especially if the same account's used for Kerberos authentication.
And what about other IDPs like Entra ID, the one that used to be called Azure AD? And what about external IDPs? The ones organizations use to handle authentication for a bunch of different applications.
For Entra ID, they mentioned the possibility of spoofing the agent by injecting a DLL into the Azure AD Connect software. Again, the goal is to potentially snag those stored credentials. And with external IDPs, well, different implementations have different weaknesses. Okta, for example, they have this Cloud9 agent that can be used for phishing. Ping might have issues with how they handle initial user linking. Entra ID, they could be vulnerable to attacks that hijack domain signing certificates, or attacks that manipulate the immutable ID attribute.
So even though these identity providers are supposed to be all about security, they themselves can become targets. And any weaknesses in their agents or in how they're configured can have a ripple effect across the whole organization. It really emphasizes how important it is to audit these systems, make sure they're locked down tight. Okay, let's move on to something that's been around forever but still keeps evolving. Email. This segment is called Old New Email Attacks, which suggests that even after all these years, there are still new ways to exploit email systems.
Exactly. Email is a mature technology, but there are still tons of attack vectors. And a lot of them come from the fact that different email parsing libraries, different SMTP servers, they don't always agree on how to interpret email addresses and headers.
They start by breaking down the basic structure of an email address in the from header. You've got the address itself, the display name, comments, grouping. But then they get into this thing about using square brackets in the domain part of the address. Why is that interesting from a security standpoint?
Well, the email standard says you can put domains in square brackets. It was originally meant for specific technical cases, but the research found that different email parsing libraries handle non-standard characters and UTF-8 encoding inside those brackets differently, and that can cause problems.
So you've got this inconsistency in how different systems understand the same email address.
Right.
And that opens the door for attacks.
Exactly. For example, they found a pretty nasty CRLF injection vulnerability in the mail address class in C#.net. It doesn't properly sanitize new line characters inside those brackets, so an attacker can inject arbitrary SMTP commands like rset to reset the connection, mail from to change the sender, rcptto to add recipients, and most importantly, data to insert the body of a whole new email. It's full-blown SMTP injection.
Wow. So you can inject commands through a malformed email address? That's classic, but this is a new twist.
Yeah.
And it's not just CRLF injection, right? They also found issues with spoofing the from header because of how different SMTP servers parse it.
Right. Different email providers like Gmail and Outlook, they might interpret the from header slightly differently. And attackers can exploit that to make an email look like it's from a trusted source, even though it's not. For example, Gmail lets you put arbitrary text in angle brackets right before the actual email address. And sometimes that can trip up Outlook's parser, so it displays the attacker's text as the sender name. They also found inconsistencies in how grouping syntax works, which can also lead to spoofing.
So even though we've got technologies like SPF, DKIM, DRRs, all designed to prevent spoofing at the server level, these parsing inconsistencies on the receiving end can still let those malicious emails slip through. It's like the mailman checks the return address, but the recipient's mailbox doesn't verify it properly. Okay, for our last deep dive today, we're going to look at accidental source code disclosure in ASP.NET apps. That's always a high severity vulnerability.
Absolutely. The research talks about a real-world case where an ASP.NET app running on ISIS, Microsoft's web server, was accidentally leaking its source code. And it came down to a combination of factors, specifically the app using cookieless sessions and a specific ISA configuration setting.
Cookieless sessions, I think we've talked about those before, right? In the context of bypassing web application firewalls. How do they tie into this source code disclosure issue?
So with cookieless sessions, instead of storing the session ID in a cookie, it gets embedded in the URL, and sometimes that can be useful for compatibility or for bypassing DOAFs, but it can also have unintended consequences. In this case, the vulnerability pops up when you've got this setting in your web.config file. Modules run all managed modules for all requests true.
Okay, that's a mouthful. What does that setting actually do?
It basically tells ISA to run all the .NET modules for every single request that comes in, even requests for static files like images or CSS. Normally, if you ask for a file from the bin directory, which is where the compiled DLLs are, ISA just handles it directly. It doesn't involve the .NET framework. But with that setting turned on, even requests for those DLLs get processed by .NET.
And that's where the cookieless sessions come in.
Exactly. The researcher found that if you crafted a URL with a cookieless session ID, you could bypass the initial 403 errors that would normally stop you from accessing those directories. So you could get to the application itself, but directly accessing bins still gave you a 404. But because .NET was now in the mix, a new attack vector opened up. ISA short name disclosure.
ISA short name disclosure. Isn't that a pretty old vulnerability?
It is. It's a legacy thing. ICE often creates short 8.3 formatted file names for files and directories. It's for backwards compatibility with older systems. And there's this tool, ICE Short Name Scanner. It exploits a specific NTFS feature to enumerate those short names even when directory listing is turned off. So the researcher, they could reach the application using the cookieless session URL they could scan.